all the dreams and ambitions, the fears and anxieties, the hundreds of billions of dollars in investment, and the innovations instantly adopted by hundreds of millions of people, all this hype around neural networks, the ability of machines to understand and generate text and images. But is that really enough to change the world, or even our own lives? We often talk about the achievements of artificial intelligence, yet we rarely stop to explain the basics clearly and calmly. So today, that's exactly what we'll do. We're going to talk about the stars of modern AI, large language models, and how they work in a way that's made the entire world sit up and pay attention. Let's start with something simple. Remember the old push-button phones with tiny screens? They often had predictive text, a basic form of auto-completion. You'd press a few keys and the phone would guess the word you were trying to type. That idea, not the phone but the method, was actually invented long before television. Back in 1905, the Russian mathematician Andrei Markov introduced a concept now known as Markov chains. The idea is straightforward. If we know that the word tomorrow often follows the word weather, we can predict with high probability that the phrase, "What's the weather like tomorrow?" will make sense. Markov chains allow you to calculate the probability of transitioning from one state to another, from one word to the next. And you can do this without understanding meaning or context. This marked a turning point. It showed that you could manipulate language, or at least simulate it, using probability theory alone. Decades later, this method was adapted for smartphone keyboards and similar technologies. These statistical algorithms could generate short, coherent phrases that resembled human speech. But there was one major problem. As soon as the sentences got longer, or the context became even slightly complex, the system collapsed. You'd end up with awkward repetitions or nonsensical gibberish. It's like trying to write a text message using only your keyboard's predictive suggestions. It remembers which words tend to go together, but it doesn't understand what you're trying to say. It can't follow the thread of a conversation. So while useful, no one took these systems seriously as a foundation for realistic intelligent speech. There was, however, more hope in a very different kind of mechanism, one modeled more closely on how humans actually think: neural networks. Neural networks aren't new either. They date back to the 1950s, and they're based on a simple yet elegant mathematical concept designed to mimic, in a very abstract way, how neurons work in the human brain. Instead of biological synapses and neurotransmitters, these networks used abstract connections and linear equations to simulate learning. But before we dive into how neural networks revolutionized text generation, it's important to understand how they differ from traditional statistical models. A typical computer program follows a strict set of instructions, step-by-step procedures, like IKEA furniture assembly guides. You've got 17 bolts, 4 legs, and a seat. Follow instructions 1 through 6 to assemble the chair, and toss out the extra bolt at the end. The programmer acts as the designer of these instructions, embedding all the logic into the code. The machine simply follows those predefined steps, with no flexibility or awareness of the bigger picture. A neural network works differently. In simple terms, it's a system made up of many neurons, small computing units connected by weights, which are just numbers that represent how strongly one neuron influences another. When the network receives input, like a sentence, it passes that information through these connections, multiplying, summing, and applying various functions. The output is a certain result. For example, after completing the next step, there is an 83% probability of obtaining a chair. But unlike traditional programming, the developer doesn't hand code how to make a chair. They don't write rules or give step-by-step instructions. Instead, they give the neural network a pile of boards and nails, metaphorically speaking, and ask it to figure out how to build a chair. At first, the network doesn't understand anything. It puts pieces together randomly, but then an external system, a teacher, like a training algorithm, compares the result to examples from a database of real chairs. The network is shown thousands, even millions of examples. How chairs look, how they're built, what they're made from. Gradually, it starts to learn patterns. It figures out that a chair probably needs at least 3 legs, that it usually has a backrest, that its height should be somewhere around knee level. All the neural pathways that led to a better result are reinforced. Their weights are adjusted to become stronger, just like in the human brain. The more we repeat something, the stronger those mental connections become. That process is called learning. The same happens here. Input, output, error, correction, repeat, millions of times. Eventually, the neural network gets good at building chairs. That knowledge, how chairs work, is now embedded in the weights between all those artificial neurons. Millions, even billions of values. That's why if you ask where in the code it says a chair has 4 legs, you won't find it. The answer is not stored as a rule. It's distributed across all the connections in the network. This ability to learn patterns instead of relying on hard-coded logic is what makes neural networks so flexible and powerful. Whether it's translating a long text, editing it, or summarizing a video, neural networks adapt. If you swap out boards for clay or nails for screws, a traditional program would crash. It wasn't programmed for that. But a neural network will try to build a chair with what it's got. In classic programming, you'd have to write endless rules to handle every possible situation. Neural networks learn those rules by themselves from data, which is why they're so good at facial recognition, image similarity, and other tasks that involve variation and nuance. But before a network can generate text, it has to understand the words themselves. Computers don't see words. They only see numbers. The word sofa or cat is just a sequence of characters to a machine. So how do we give words meaning in the digital world? Text tokenization is like DNA sequencing. A long strand of DNA has to be broken into readable units, nucleotides or codons, before it can be analyzed. Similarly, language is broken into tokens so the model can read and interpret it, whether those tokens are full words or just prefixes and suffixes. Next, we need to convert these tokens into numbers so the machine can work with them. This process is called vectorization. Usually at this point, people start talking about 1,000-dimensional spaces. But the idea is simpler than it sounds. Imagine assigning a bunch of numbers to each token, where each number represents a property. One number could represent living or non-living. Another might measure positivity or negativity. Another could describe size. Once we assign hundreds or thousands of these values, the model can see tokens not just as numbers, but as rich representations of meaning and context. The final numerical representation of a token is called an embedding. That embedding is learned the same way we taught the network to build chairs, by feeding it millions of text samples and letting it adjust the weights over time. We don't define what each dimension means. The model figures that out on its own. But intuitively, we can say that cat will end up closer to dog in this space than to car or sofa. Now, it might seem like we've done the hard part, breaking down language into components and giving each piece meaning, but that's only half the challenge. Language is sequential. The order of words matters. I bought a ticket, got on the train, and rode to the station. Here the sequence is crucial. Getting on the train comes before arriving at the station. Classic neural networks struggled with this. They don't have memory, only static weights set during training. That's a problem. To address this, scientists developed recurrent neural networks, RNNs, models that pass state from one word to the next. As the network reads each word, it updates an internal memory. Word 1 modifies the state, then word 2, and so on. This allowed the model to remember previous words in a sentence. This approach revolutionized machine translation. If you remember, when online translators suddenly started improving dramatically, that was because of recurrent neural networks. Sentences made more sense, but there was still a problem. The longer the sentence, the more memory the network lost. It struggled to hold on to information from earlier in the paragraph. And because RNNs processed words one at a time in sequence, training was slow and inefficient on large data sets. Eventually, we hit a wall. We could translate sentences and captions, but understanding meaning, holding entire conversations, grasping context, subtleties, wordplay seemed decades away. The technology just wasn't there, or so we thought. Like the rest of the world, we didn't yet realize that the seeds of the neural revolution had already been planted, and they were about to break through. In 2017, a group of researchers published what is now clearly a landmark paper. Its title, "Attention is All You Need." It introduced the transformer architecture, a new kind of neural network that combined the best elements of previous approaches. The core innovation, as the title suggests, was the attention mechanism. Instead of processing text from left to right, the model learned to look at all the words simultaneously, paying attention to how each word is related to the others. A sentence like "the cat sits on the mat" started to make more sense to machines. The model could recognize that the word "sits" is closely related to cat, because who sits? And it would see that "on" connects with "mat," revealing spatial relationships. This understanding comes from token embeddings, numerical representations of each word, through which the attention mechanism detects patterns. It's as if each word is looking at all the others, calculating the strength of their connections. Now, instead of reading text piece by piece, the model can process everything at once. That's the game changer. Transformers allow for parallel computation. They don't read text sequentially, they absorb it all at once. This massively accelerated training in data centers, and that speed unleashed a chain reaction. The more data you feed these models, the more their hidden capabilities emerge. Their main strength lies in self-attention. The model doesn't focus on everything equally, but prioritizes the most relevant parts. You alternate traditional neural network layers, like the ones we used when training chairs, with attention layers. Enrich the data, while attention helps determine which parts matter most, like ignoring the color of a chair's wood and focusing on its shape and construction. This allows models to do more than memorize and repeat. They learn to draw deeper insights from the relationships in text. The more attention layers a model has, the more complex the associations it can detect. One layer captures grammar, another finds meaning, another identifies stylistic nuance. Transformers build an internal structure of a text, keeping track of its flow even across thousands of words, while still zeroing in on a single word and interpreting it in context. That's why modern AI is so much more than a glorified autocomplete. Think of old T9 that predicted the next letter in a word. GPT, trained on billions of words, can expand on your ideas, answer questions, and reformulate thoughts, as if it actually understands what you wrote. This goes far beyond simple autocompletion. Enter large language models, powerful systems that can perform a wide variety of tasks if you know how to ask the right prompt. And now, many of them don't even need a prompt. They're built right into everyday services, ready to anticipate your needs. Since training these models requires colossal computing power, only major companies and institutions could afford to scale them to trillions of words and translate that into network weights. After that, it's just engineering. You get a universal engine that can be fine-tuned for specific tasks, answering calls in customer support, not with scripts but real responses, writing product descriptions, summarizing news. GPT-like models began infiltrating every field where text ever played a role, even if you didn't notice. Let's say you're searching for a date spot and type "restaurant." Several neural networks kick in. One interprets your intent. You probably want a place nearby, not just the definition of the word. If you're curious about Michelin stars, you get not just a list of links, but an answer, a summary pulled from websites. Ask a follow-up question? It keeps the conversation going. Search isn't just digging deeper anymore. It's a dialogue with an AI, explaining concepts patiently and in multiple ways. Some may remember, in the 2000s, there was a search competition where people had to find answers, not just facts. That required skill in writing complex search queries across any search engine. But now, LLMs are reshaping even that core tool, online shopping. The hardest part? Interpreting reviews. Popular products have thousands of opinions from real users, not professional reviewers. Neural networks analyze these comments, summarize key points, and show what people like or dislike instantly. Want to know what's in a long video but don't have the time? Now you get a summary. Interested? Too tired for subtitles? Use AI dubbing. One model translates, another generates a natural voice. Language models are fundamentally changing how we interact with machines. Smart speakers used to recognize voice and spit out pre-scripted answers. Now, you can give them flexible commands. Turn off the TV station when the match ends. And it's a generative language model that interprets that, not a preset script. What used to be a glorified remote control is turning into a hub for managing your whole life. Want your room at the perfect temperature? AI coordinates your humidifier, heater, and AC all at once. Here's where Arthur Clarke's famous quote comes in. Any sufficiently advanced technology is indistinguishable from magic. But there's a flip side. Once you understand the magic trick, it loses its mystery. You begin to see the edges, what this tech can and can't do. One common mistake, believing that large language models are some kind of super encyclopedia storing facts like a database. As we've discussed, neural networks don't store answers, they generate them. Simplified, they learn relationships between words, phrases, and concepts and build responses on the fly, like someone who's read so many books they can formulate a sentence without quoting, just synthesizing what they've absorbed. But keep in mind, machines don't have real experiences. They can hallucinate, write confident, well-structured nonsense, and it can look very convincing. The difference between truth and fiction? Whether the training data happen to include enough relevant material. In neither case is the model retrieving an answer from storage. That's why giving models access to the web and live search engines was a big deal. Answers became more accurate because the model could draw from real-time information. But still, the final answer is generated by a neural network. That means flexibility in phrasing, but also potential mistakes, especially if source data is unreliable. So for mission-critical tasks like legal advice or medical diagnoses, you absolutely need human expertise. A language model can give you a solid starting point, but it's not the ultimate source of truth. Another key point, these models don't have long-term memory. Once a conversation ends, the slate is wiped clean, unless an external service tracks your history and feeds it back in. The model itself doesn't update its training or remember preferences unless programmed to. And finally, creativity. A language model won't think, what if I break all the rules and invent something conceptually new? It doesn't explore the world asking, what's never been done before? It sees language as a probability game. Creativity is just clever statistics, but inventing an entirely new scientific theory or crafting a story twist that feels fresh and original, that's still beyond it. If the goal is to explore variations on a theme, though, like inventing new literary genres, language models shine. They can toss out dozens of ideas, drawn from everything humanity has written, but without human judgment, conscious rule-breaking, and a deep desire to break the mold, you won't get revolutionary breakthroughs. That's where we come in. LLMs help people make connections they might not have seen on their own. They expand your intellectual reach, augmenting your thought process. You can debate whether AI is really intelligent, but one thing is clear: neural networks are already changing how we communicate, search, create, and maybe even how we think. Is that enough to call it a technological revolution? To answer that, we'd need to understand the rest of the picture: how neural networks handle images, video, music, prediction, how they impact daily life and science itself. Thank you for staying until the very end. In a world where attention is the most valuable currency, I truly appreciate yours. If you found this video thought-provoking, leave a like and a comment. It helps it reach others who are asking the same questions. See you soon, and may doubt never leave your mind.